So just to summarize, our delta term, we computed these delta terms for each layer starting from the output layer L and then going backwards to layer L-1, L-2 and so forth. And we just added L-3 here just for more clarity. And we saw that once we compute the delta term, because each delta term is associated with a neuron, once we compute the delta term for every neuron in a given layer, we can use it when we backtrack to another layer. So we see here, once we computed delta I at layer L for every I going from 1 to n, we can reuse those delta terms here. And once we computed the delta j terms for all the neurons in layer L-1, where j goes from 1 to n, we can reuse the delta j terms in layer L-2, and then we can compute the delta k terms at layer L-2 and reuse the delta k terms at layer L-3. That way we get to reuse calculation. We don't recompute this term over and over again here, and we don't recompute this term over and over again here, and so on. Now, if we examine our delta terms, we see that with the exception of the delta term in the output layer, the progression in the delta terms for layers L-1 and L-2 and so on also follows a distinct pattern. We see that for a given hidden layer, indexed as hidden layer, lowercase l, and if you consider the jth neuron in hidden layer lowercase l, then the delta term of the jth neuron in hidden layer l, lowercase l, is given by the sum as I goes from 1 to n of the delta terms of the neurons in the layer before it, that is hidden layer lowercase l plus 1, times the weight going from neuron j to neuron I in hidden layer lowercase l plus 1, times the derivative of the activation in neuron j of layer l. Now this was the case when our hidden layer is between 1 and uppercase L-1. That is when we're not at either the input layer nor the output layer. In the input layer, as you recall, we take in the input vector, meaning each neuron takes in as input an entry from the input vector. And we omit calculating delta terms for the input layer. And the delta terms at the output layer is given by this expression. So we can summarize a full formula for our delta term at neuron j in some hidden layer L as, and once we computed all of these delta terms for every single layer, if you're given the task of computing the partial derivative of the cost function with respect to some neuron, let's say I, going to neuron j in hidden layer L, that is W ij L. If you're tasked with computing the derivative of the cost function with respect to this weight, all you got to do is go back to all the delta terms you computed, find the delta term for this neuron, that is delta j at L, and then multiply it by the activation at neuron I. So that is AI L-1. So if you compute all these delta terms, we automatically get the derivatives for free. So now we found a generic expression for any weight derivative in our network. Now the question of where these delta terms get stored as they're getting computed is something we'll circle back to when we start employing vectorized notation. So that is step 3 of our strategy, to derive the backpropagation equations. But for now, we have completed step 1 of our strategy. Now the next step entails finding generic expressions for the bias derivatives, that is the partial derivative of C with respect to any arbitrary bias term within our network. And this step will be fairly similar to step 1. So let's continue with step 2.